Okay, so you may have noticed that when we discussed correlation before and we did the test, we usually talk about assumptions for a test and we didn't give any assumptions. That's because the assumptions are a little bit more complex. As this is strongly related to regression, we have the regression assumptions. So these include linearity. Obviously, our data are linearly related. Otherwise, as per my kind of profit loss drunken darts player examples, you have a relationship, but it's not linear. So this test really doesn't work. Um, there's a degree of normality. Now, this statistical assumption, you can have a correlation without a statistical test. So the correlation is meaningful without doing the significance test. But generally, for small samples, we want normality for a t-test, so it's the general t-test assumptions. And generally, as per regression, we don't want what I showed you with the movie example of what we call those kind of almost heteroskedastic errors, where the errors are getting bigger as your x gets bigger. But we'll talk more about that in the regression chapter. For the moment, just think if we meet the assumptions, we have completely continuous data, then we can do the Pearson's correlation, which this is called the Pearson's correlation, and we can do the test for the correlation. In fact, there's multiple tests for the correlation. There's one that involves a z-score as well, but we just did the basic one with the t-test. Now, if we don't have normality, we potentially have outliers, we maybe have categorical ordinal data, then we have specific methods for categorical data, the Spearman's correlation and the Kendall's tau. We could also do kind of what we call robust statistics, but that's a little bit beyond and bootstrapping, but that's a little bit beyond this kind of simple course. Okay, so let's go to SPSS. So I've just loaded, this is the IHNO data set. This has got like the math quiz in that we had before. So it's almost going back to what we did previously. So we'll start off with something we actually did previously. We're going to go to Chart Builder. And we're going to go to Scatter Dot Plot. And we're going to do the matrix. Now, you can't see too many variables in the matrix. But let's stick with what we had in the slides. And we'll go with the basic. It doesn't really matter, but we'll go with the basic math quiz. We'll also add, I want to kind of have them all selected at the beginning actually. So we'll have heart rate pre and heart rate post and two of the anxiety measures, base and pre. Let's just throw them all in here. Okay, let's try that again. Okay, some reason it wasn't. I think you have to make sure you hit it at the left. Click OK. Now double click on it. And we've got the option to add trend lines. So we're going to add trend line here, add fit line. And it should actually do a fit line for each of the individual regressions. Now close it. So we have to go back to the output, and there we go. So you can see the relationships here. Now there's some of the items, for example, if we look at math quiz, we don't have strong correlations. We seem to have slightly negative relationships between math quiz and some of the heart rate measures. But we can see that these measures are kind of correlated with themselves. For example, heart rate pre and heart rate post have a pretty strong relationship. And also the two anxiety metrics, anxiety pre and anxiety base, have a relationship. So we kind of expect that when we do the correlation. So now what we want to do is we want to calculate correlations for these variables. So we're going to go to Analyze, Correlate, Bivariate. Now it works a little bit like the scatter plot matrix. So we add the math quiz. We're going to add the same as before, heart rate pre and post. And also the first two anxiety metrics. We're just going to kind of click the basics. We're going to do a two-tailed test. We're going to flag significant correlations. Then we're going to stick with the Pearson. And here we have it. So we have a table here. Now notice we could have, one of the options was only to do half of these a triangle matrix, because you can see, for example, that math quiz and heart rate pre has exactly the math quiz on the row and heart rate pre on the columns has exactly the same values as math quiz on the columns and heart rate pre on the rows. So it's a symmetric. So let's look at heart rate pre and math quiz. You get three values. You get the actual correlation, the effect size. You get the significance, which is P. We'd reject the null hypothesis of the correlation not being significant at P equals 0.05, but fail to reject at P equals 0.01. And we've got a sample size of 85. We can see probably about the strongest correlation is between the two anxiety metrics. So anxiety pre and anxiety base has a correlation of 0.561, and it's significant at the lowest, P level. P is less than 0.01. And we can also see the two other heart rates are actually significant. The heart rate pre and the heart rate post, again, a correlation above 0.5, P is less than 0.01. And to help us, we have a star if the P is less than 0.05, and 2 stars if the P is less than 0.01. Similar to kind of some of the other statistical tests. Okay, so let's kind of go back to the slides. Just a summary, as I said, correlation is an effect size. We talked about that before. We can have, for example, small effect is 0.1, medium is 0.3, and large is 0.5. Very, very simple. That's one of the issues with effect sizes. Remember, we had the 2.5, 0.2, 0.5, and 0.8 for the Cohen's d. Each effect size has different values. There's nothing standard there. We've got the coefficient of determination, R squared, which is a squared value. And I know some statisticians don't like this definition, but this is, and we'll talk more about this in regression, but this is the proportion of variance in, usually you would say the proportion of variance in X accounted for by the regression. Sorry, the proportion of variance in Y accounted for by the regression. But as regression as correlation goes in either direction, you can say the proportion of variance in one variable that's accounted for or shared by the other. But at the moment, correlation is basically our inference. We can kind of infer that pre-release social media buzz is going to be causing revenue on the opening weekend. It's very unlikely that the opposite is going to occur. In fact, it's impossible because of the kind of temporal time difference, one being later than the other. Okay, so we can have non-parametric correlations where the data are ordinal. And let's just kind of give a little example here. We have Spearman's rho and Kendall's tau. And we've got several paintings here. And we have two critics. And their critics note this is an actual ranking of paintings. So the first rated one is 1, then the next rated one is 2. So critic 1 likes painting 2 the best and painting 5 the second. Critic 2 likes, let's just get a different color. Critic 2 likes painting 5 the best and painting 2 the second. So you see there's not perfect agreement, but you can see that, there's general agreement as well. You see like critic 2 likes painting 6 in 9th place, and critic 1 has that painting in 10th place. Let's get back to red. Now note, these are rankings. So this is a simple example, but I'll put, if you don't have rankings, you need to rank the data. that would be important. So, say for just an idea of ranking, say I have, say I was rating out of 10 and I had rank of 0. Sorry, if I had gave a score of 1 to 10 of 1, 3, we had 2 3s, a 5, a 7, and an 8. This is kind of ranked high to low. So, you know, my first ranking would be, and you could rank in order, you can rank opposite. So going top to bottom, this would be 1, 2, 3, 4, and 5. So both of these would be 4.5, and this would be 6. We'll talk a lot more about rankings when we do non-parametric statistics. And of course, you could rank low for high. That would be 1, 2.5 for these two, 4, 5, and 6. Okay. In fact, with this method, whichever way round you rank, you should get the same value. So anyway, we do the rankings. You calculate the difference between the rankings. So the difference 4 minus 5 is minus 1. 1 minus 2 is minus 1. We calculate the actual difference. So the first minus the second. Minus 1, minus 1, minus 1, minus 1, 1, 1. Some evens, then 2, and then 0. And then we also calculate the squared rankings and calculate the sum of squared rankings. So we just square all the rankings and add them up. And then the final formula for the Spearman correlation is given here. Now, just note a few things. The correlation is still between 1 and minus 1. So this 1 minus 6 times the sum of all the DI squares divided by the normalizing factor. Now, if there's no difference between the ranks, so if all DI equals 0, so we had perfectly matching ranks, then this here would be 0 and RS would be 1. But it's a bit easy, it's a bit harder to prove, but if the rankings are opposite, so if rankings are kind of opposite, and I might get you playing around with this on the homework, I just give myself, I always seem, the teaching class inspires me to set interesting or difficult homework exercises. So if the rankings are almost opposite, this would be kind of 2 and RS would be minus 1. So it doesn't seem like it's similar to, the calculation is different from the Pearson correlation, but it kind of works in the same way. If you've got perfectly ranked the same, then we have a perfect correlation. And I put 2 there. If everything's opposite, then we get a correlation of minus 1. So let's go back a little bit and go back to the critics. So let's calculate this. So it's 1 minus 6 sigma, and then again I equals. I always like to put the kind of the iterators in. Di squared all over n squared minus 1, which is 1 minus 6. We've just calculated sigma d squared here, all over, the maximum possible. So that's 10, 100 n squared minus 1. And that gives us 1 minus 60 all over 990, which is equal to this. It's quite a strong, and we can see it's a strong correlation. Again, these reviewers these critics are very similar in their rankings here. This is the same ranking, that has the same ranking, 2 and 1, 1 and 2 are very similar rankings. Everything has very similar rankings. So this is not a surprise that we have a kind of a very strong correlation here. Just a couple of little final things on the correlation. This is from the other textbook. This is from our business stats textbook, and it's basically saying that the Spearman correlation is the same as the standard correlation, But these were the sum of squares formulas we used for the standard correlation using ranks. So these are the ranks and these are the average ranks. Now, I've played around with this and it doesn't seem to quite match this formula here. There seems to be a very slight difference or some sort of correction missing. So if I ask you to do a Spearman's correlation in the homework, and obviously I've not done a worked example for this and this is harder, so I would do this particular formula. It's very easy and kind of self-explanatory. But do remember, if you don't have ranked data, then you will need to actually rank the data. Okay, so final little thing on this video. As I said, partial correlation, for some reason I did in the previous year, so that's going to be a separate fourth video. Let's kind of go back to our correlations. So let's just do analyze, correlate, bivariate, and let's just do every type of correlation at the moment and just see how similar they are. So let's just look at the ones we looked at first. So the math quiz, which was marginally significant with Pearson. For Kendall's, it's still marginally significant. In fact, it's a little bit more powerful. The significance is 0.02. For Spearman's, again, 0.019, a little bit more significant. Let's look at heart rate pre and heart rate post. So that is 0.527 for the standard correlation. Now notice, it's a slightly stronger statistical test, that the actual correlations are a little bit lower here. So for the math quiz and heart rate pre, the correlation is minus 1.79, but a bit more significant. And here for the Pearson, the correlation's a little bit higher, but it's a little bit less significant. And the heart rate pre and the heart rate post, here again, the correlation's actually lower. But again, they both have this we can't compare the significance, but they're both less than 0.01. And heart rate and pre and heart rate post for Spearman's, it's a little higher than Kendall's, and again, very significant. Look at the two anxieties, 0.43, very significant, 0.347, very significant for Kendall's. So generally, the magnitudes of the correlations are a little bit lower for the non-parametric, but they just seem to be slightly more significant. Now, you can actually use the non-parametric in a parametric setting. That's generally not considered to be the thing to do. But if you have ordinal data, you have a small sample size with non-normal distribution, then you would go for the non-parametric correlation. And that is it.